My name is Ursula DeMarco. I'm a research scientist at the American Museum of Natural History in New York City. My research involves the physics and astrophysics of stars, their evolution, their binary nature, and their nebulae. Planetary nebulae, the particular nebulae I work with, are some of the most beautiful objects in the sky. Nobody's really been able so far to figure out why we have some that are perfectly spherical and some that are like all over the place. So that alone is a good reason why, I love to study them. Planetary nebulae are thought to be ejected by single stars at the end of their lives. I have a strong feeling, and I'm not the only one, that this is not true. That planetary nebulae are actually ejected by a system of two or more stars that are gravitationally bound, and they are born together and they remain together over their lives. This would make them very different objects from what we think they are today. It would rewrite Astronomy 101. Stars, like the stars I study, the hot stars, shine primarily in the ultraviolet. So if you want to observe them and study them and understand them, you really need an ultraviolet instrument, in particular an ultraviolet spectrograph. When STIS, one of the current instruments on the HST, broke, we lost UV capability, ultraviolet capabilities. So when STIS went down, that was that, And now not only STIS will hopefully be fixed, but costs another ultraviolet spectrograph, even more sensitive and much better, is going to be installed. I'm hoping that the TAC, the Time Allocation Committee, sees that if this project is done, it will be a significant step towards understanding whether planetary nebulae derive from binaries or from single stars.
It's very difficult to write a good proposal. I think that it's a combination of scientific expertise and marketing and putting it in language that somebody who isn't an authority in your field is going to understand, and that they're going to appreciate the importance of the science that you're trying to do.
I'm extremely nervous about the proposal and the evaluation process. I know the dates when the committee is going to be gathering. It's nerve-wracking. It's a big deal, our career rests on this.
My name is Michael Strauss. I'm the chair of one of the panels reviewing and judging the Hubble Space Telescope proposals. The Time Allocation Committee is made up of astronomers from both the U.S. community and from abroad as well, all working together to judge these proposals. There are 958 proposals for telescope time. That's about 6 times the amount that we'll be able to allocate, given the amount of time there is. Our job is to choose the best science projects, and the new scientific opportunities with the COS and the WIFC-3, the 2 new instruments that are being put on to Hubble. There's a huge excitement in the astronomical community to do that, and it's our job to choose the best proposals along those lines to take advantage of those new opportunities.
Oh, poo bollocks. I am annoyed because, if you work a lot on these proposals and you don't get it, it feels certainly like the time was wasted. And they give you, the reasons to why it didn't pass. You propose, you submit, and you're happy. Then you let 1 month go through, and you read it before you have the answer, and you actually realize that it's not perfect. And if it's not perfect, it doesn't have a chance. With every proposal, even those that don't get time, you improve, and it means that this proposal next round will have a much better chance than if I had decided I won't propose this time. It delays one direction of my studies, and that will mean that I have more time to concentrate on other studies, and then next year I'll try again. You're not going to stop because a proposal doesn't get through. You're going to get at it next year and do it better.
My primary field of study is planetary astronomy, and I'm most interested in the outer solar system, things that lie beyond Jupiter. That part of our solar system holds a lot of clues to how our own solar system formed and how it got to be the way it is. The wide field camera is going to be very useful for people who are studying the Kuiper Belt because it'll allow them to see more objects over a wider field. When we're studying the planets in our solar system, we're most interested in high-resolution capability, getting the best pictures that we can get. And so having the new cameras helps us in that regard.
If you look out in the universe, you see stars and you see galaxies. That only forms a very small fraction of the universe. About 2% of the universe is the matter that we can actually see, and the rest is dark. That dark matter imprints on the images of very distant galaxies. From that we can detect this very weak signature that dark matter is imprinting on these galaxies. This signature is called weak gravitational lensing. The new instrument that's going to be very interesting for lensing is WIF C3, the Wide Field Camera 3 in the near infrared channel, because that helps us look even deeper into the universe.
My field is the evolution of the universe as a whole coming out of the Big Bang, but in particular the formation of galaxies. Galaxies are really the building blocks of our universe. I believe that the new instruments will have a huge impact. We're going to be looking farther back in time, and this will allow for the first time a large census of galaxies when the universe was just 2 or 3 billion years old. That turns out to be a very critical epoch in the history of the universe.
The Wide Field Camera 3 will enable us to study much fainter objects, especially in the infrared. That is a light that is longer wavelength than the visible light, and the most distant galaxies, the ones that are further away, the ones that we see closer to the time where the universe is being formed, they appear to us in infrared. The expansion of the universe stretches the wavelengths, and we see them longer than we would see them otherwise.
The universe evolves extremely fast at those early times, and so Wide Field Camera 3 will make the difference between seeing truly infant galaxies and the somewhat toddlers that we're seeing today.
Hubble laid the groundwork that you can do things in space with a telescope that wasn't planned to do that observation. We have pushed the instruments to a level that wasn't expected, even by the people who built the instrument. Hubble has made huge advances in this field of planets orbiting other stars. And in particular, Hubble made the first discovery of an atmosphere around another planet outside of our solar system.
For the first time in history, we were studying the chemical composition of other planets. And of course, that really is the bright future of extrasolar planets, learning their nature and especially whether they have signs of life on them.
If there were no Hubble, we would have known from some of these repetitive measurements on the ground that there are planets orbiting other stars, but most of the ones known would be very close into the star, closer than Mercury is to the Sun, which means that they're very hot planets, not places you'd care to visit.
We learned a lot about the outer solar system from the Voyager flybys in the mid-1980s, but they really gave us just a quick snapshot of planets that turn out to be really very dynamic. Hubble has provided some of the most spectacular imaging of outer planets that we've been able to get, aside from sending a spacecraft there. Its fabulous resolution allows us to see details in the cloud patterns. It allows us to study the moons and the ring systems of these outer planets with unprecedented detail. It's really been a workhorse for the Outer Solar System astronomy program.
We know that the galaxy is there based on a ground-based picture, but it's a blob. Hubble is able to take pictures of the galaxy, and not only a single picture, but sharp pictures at a whole bunch of different wavelengths. And every wavelength has a different story to tell. Hubble will be remembered for discovering black holes in nearby galaxies, taking the first high-resolution pictures of the early universe, and I think for many contributions on star formation.
We as scientists should learn from the Hubble experience that it's very important to communicate to the public what we do. And Hubble has done a really good job at that. I mean, it's easy because they're stunning pictures, but there's also a lot of work that goes into that.
In some perverse way, Hubble's impact has been heightened by the fact that it went through trouble. That brought it to the public's attention, and the fix was dramatic and involved a human interest element that makes the telescope larger than life. It's more than just a telescope for the average person. It also becomes a symbol of American know-how.